screen because you want to show the presentation or not?
I can share it now, guys, right?
No. Just wait a second, but I need to ask about that you need permission to show it. Może pan udostępnić, żeby mógł szerować prezentację? We will check it. Okay. So, all the viewers are on YouTube. I'm here on Zoom, so I gonna listen to. Hello, everybody. It's ScienceCon Online here. I hope that you already eaten your lunch and you are ready for the next part of our event. ScienceCon Online is a unique 3-day-long event that focuses on planning a career in physics that answers the world's most pressing challenges like climate crisis, space exploration, and emergence of digital society. And we reached the last day of our conference before the final presentations of all our participants that are here stationary in Kielce in Chęciny at European Center for Geological Education. We're gonna host the last lecture by Mr. Gustavo Abade from University of Warsaw about the atmospheric clouds challenge. Mr. Gustavo is with us. Hello, good afternoon, and the stage is yours. But before we start, before you're gonna share your screen, I would like to add that you can ask your all questions in the live chat under the YouTube transmission, and we'll ask them at the end of our presentation. Mr. Gustavo, here we go.
Looks very turbulent and very complicated. Okay, so then this is more or less that seems to be a complicated system, and in fact it is, right? So, and based on that, I will just use some two quotes. Very turbulent and very I will start from a very influential philosopher of science. So you probably know about Caustic, and he wrote a nice essay called Of Clouds and Clock, when he was talking about determinism and indeterminism in science in general. And here's his quote, right? So in this book, he said, "My clouds are intended to represent physical systems which are highly irregular, disorderly, and more or less unpredictable." So, and then on the other screen, he says about a precision clock that represents a physical system which are regular, orderly, and highly predictable. So physical systems are between those two extremes, right? So for example, the position of planets in our solar system are more predictable. So they are more like clocks than clouds. And clouds are really to represent a very complicated thing, something which is unpredictable, right? Even the common sense view of things. So then the picture that we have a cloud is something very complicated. And a second quote that I will mention, so it's based on this book here. So this is by an American cartoonist, Zach Weinersmith. And then in this book, he tries to summarize in a funny way, so major fields of science. And he's the statement about the physics, right? So you probably have observed this in some social media, this kind of quotes. So summarizing the field of physics, he says that Aristotle said a bunch of stuff that was wrong. Then Galileo and Newton fixed things up. Then Einstein broke everything again. Now we've basically got it all worked out, except for small stuff, big stuff, and a lot of stuff, right? And among those stuff that are not very precise, he mentioned Einstein broke everything again. Now we are the concept of got it all worked out. So the point that turbulence is except for small stuff, big stuff, problem in physics, in classical physics, and there is still among those stuff that are not very precise, he mentioned Einstein. Why we are talking about that? Because clouds is something like this, right? So we have complex microphysics, so many microphysical processes here that so we have some dust, right, entering here the cloud, creating cloud droplets, right? Those cloud droplets, they freeze and generate ice. So we have ice crystals that they aggregate and form very complicated shapes of aggregates, right? Those things break up, they evaporate. So there are many microphysical processes here happening, right? So we have really a many-body problem here. And on the top of that, we have turbulence, right? Which is a huge problem. Okay, so then cloud is this complex microphysics interacting with turbulence. That's why this is so complicated. Okay, and this is a challenge to model this because of what? Because of a multitude of scales that we have. Okay, so for example, a convective cloud is something big. So this is a tens of meters. Okay, and at the same time, those cloud particles, those hydrometeors that we call, right, dust, cloud droplets, drizzle droplets, rain droplets. So they are very, very tiny objects. So they are very small compared to the whole scale of the cloud. And we have other scales here, like Kolmogorov scale, which is the smallest scale related to a turbulent motion, right? And then we have this wide range here of scales. Here I present this length scales, but also there are associated time scales, right? So here the time scales of the largest length here is about hours, right? So the evolution of a cloud. And we have here, for example, activation of cloud droplets, they are as in the fraction of seconds. So also a multitude of time and length scales. Okay, so then the microphysics operates here. So microphysics operates at small scale, so the interactions of cloud particles. And on the larger scale, so this is the solution of the flow, involves what we call the dynamics, right? That involves the time scales here, including the inertial subrange of turbulence. Okay, so then this is the challenge. Okay, so then I'll just concentrate on 2 or 3 problems or aspects of the difficulty related to simulation of cloud, right? And to understand. So the first problem is what happens is the hydrodynamic instability. So this is more thing related to this cauliflower shape of the cloud top, right? That every child, right, drawing a cloud, draw this shape, right? And then we can analyze it very quickly in a very simple situation. For example, imagine a rising thermal. So imagine here that you have the atmosphere, and then you create a kind of a balloon, right? So this is a warmer bubble of air. And because of buoyancy, so this warmer bubble will go up. So exactly the convective motion associated with the cloud. So this is described by Navier-Stokes equation. So we can simplify the description by assuming that this warmer bubble here is just a small perturbation of a base state, so of the static atmosphere. So doing some manipulation, so the equation here takes this form, and the motion is driven by buoyancy. Buoyancy appears here as a term here on the right-hand side. So inside the warm bubble, so this is positive, and outside this is 0, and then it goes up. Okay. So then of course, it will evolve. So we start from a circular shape here, and at the end, if we look at the streamlines of this motion here, of course, after 3 minutes, so it's already deformed, okay? And then the flow, it starts to complicate. So we have this kind of structure here. And then if we look at these arms here, right? So it starts to appear the instabilities, okay? So look, that is not a very smooth thing, but you have some amplifications of perturbations here. And then it starts to appear those vortices here, right? So we have the engulfment of the air outside the cloud entering the cloud. So this is exactly that generates this cauliflower shape. Okay, so then you see the instability, this is the hydrodynamic instability evolving here. And this is a 2-dimensional picture. So if you go to the 3 dimensions, so we have here the transition to turbulence, right? So this is the initial bubble, then evolving to something like this, right? And then you see that this resembles this cauliflower shape at the interface between the cloudy air and the clear atmosphere, okay? And the transition of turbulence is more or less, we can see here, for example, entropy production. Entropy is a measure of vorticity, of angular rotation of the fluid particles in the flow. So at the very beginning of the motion, it was induced by baroclinic. So this is more due to this buoyancy and the difference and the gradients of temperature, right, inside the bubble. And then it starts to dominate by the vortex stretching. Okay, so vortex stretching is a mechanism that changes the vorticity of this, and that leads to the transition to turbulence. So here, this is the way that the major way of generating turbulence in the cloud, right? And of course, that this turbulence here will interact with the microphysics, so with the cloud particles inside. So this is the main idea about the instabilities, right? And about the turbulence generation in a cloud. Okay, so just one aspect. So we have many other sources of generation of turbulence in clouds, but let's focus on this one. So there is another problem. So the second aspect is the problem of rain initiation in warm clouds. Okay, so what is the issue here? So the schematic of a cloud here again. So this is just a plume that is generated by buoyancy, right? So the ground here is, we have warm air that by buoyancy goes up, and then it carries some particles. So we call this cloud condensation nuclei. So it can be dust, right? Or some salt if you are in close to the ocean or the sea, right? And then, of course, when you go up, the temperature decays, the pressure decays, and at some point, the vapor pressure here is larger than the equilibrium one, and then this vapor tends to condense into this cloud condensation nuclei, and will create and will produce the droplets. Okay, so these are the cloud droplets that will generate the cloud. And in this simpler picture here, we have two important microphysical processes. The first one is the condensation. So it's the diffusion of the vapor, right, in the air to the droplet. So it grows by condensation. And this is one mechanism for creating the cloud. And the second one, which is more important for rain, right, to get rain from the cloud, is the process of coagulation. So we have two droplets that will collide and coalesce and produce a larger one. So this is the main mechanism in warm clouds. I mean warm, that clouds without any ice particles, right? So we have only liquid droplets. And by coagulation, we form larger and larger droplets, right? That they will be so large that will start to sediment and generate the rain, okay? Okay, so then this is the simplest mechanism in a warm cloud. So, of course, the problem is so complicated that we have to simulate this on a computer. So the simulation looks like this. So we have here just a contour of such a cloud. So there's a cloud have a deep convection, right? So this is the cloud base. It has evolved. So we have a cloud like this. And to obtain this cloud, we had to resolve the Navier-Stokes equation, right? Therefore, the flow induced by buoyancy and stuff like that. And of course, since we are doing on a computer, so we have to do it in a discretized grid. So here you see that we have to solve the numerical equations in a grid, right, which has a limited resolution. So here we have the velocity field, right, at some points of the grid. And look that this here in red is what we call a grid box. So this is the smallest length scale that we can represent in a numerical simulation, okay? So look that this is a huge object. So we have something like 5 kilometers here. And then we have to introduce as much scale as we can, right? So normally, so the size of this small square here is something like this. So the simulation grid box is of the size of tens to 100 meters. Okay, so the resolution is not very good. So unfortunately, because of a limitation of our resources. And if we look at how many droplets we have in such a small grid box, in the resolution grid box, so we have a large amount of droplets. So this is a huge number of objects here, right? And we have somehow to model this. So to solve the rain initiation here, so the collision and coalescence, okay, between those droplets. And just to mention where we get this size of the box. So here to have a systematic kind of simulation. So this size here we have to take in this what we call the inertial range of the turbulence. So the cloud turbulence has an spectrum, an energy spectrum here as a function of the wave number. Okay, so the energy dependent on many scales of the flow. And in this inertial range, so it has a more or less a universal decay. Okay, so this is something that we know from Kolmogorov theory. So this is not perfect, but this is very useful. So then the resolution that we take in what we call the large eddy simulation is a length which is here in this inertial range of turbulence. Okay, but the problem that I would like to mention is that the rain initiation, right? So we have somehow to understand the physics here, or to simulate the physics of collision and coalescence between such a large number of droplets. So the idea is that it's completely impossible for us to simulate the trajectory of each element here and resolve the collision and coalescence. Okay, so we have, unfortunately, we don't have the resource for that. Even with the most powerful computer, we cannot do that. Then we have to do a kind of a probabilistic approach to solve this problem. Then the probabilistic approach, the problem is the following. So what is the probability that this droplet pair here, so that is in darker blue here, in this volume of our grid box will coalesce in this short time interval? So the probability is something like this, that this is written in terms of what we call a collision kernel. Okay, so this is the main object in the probabilistic description of collision and coalescence of droplets. So of course it depends on the droplet size, the distribution of sizes here, on turbulence. Okay, so we have those particles here are immersed in a turbulent flow, and we have this big problem to evaluate the collision kernel. Okay, so once we have such a probability, imagine that we know how to calculate that. So we can use, for example, a kind of a Monte Carlo method. Okay, so what we do, so we calculate this probability. So look at those cloud, this pair here, and you want to check if they will collide or not. So we calculate the probability here, and we take a random number from a uniform distribution from between 0 and 1. Okay, so we all know how to do it. If this probability is larger than the number, then this random number, then we coalesce those droplets. If not, so we leave them without coalescence, and then we go the next time step. So this is the simplest kind of a probabilistic way of simulating collision and coalescence, of simulating rain formation, right? But the issue is how to calculate this collision kernel, okay? And then the problems start, right? So the classical approach, which is what we call the gravitational collision kernel. So this is the classical collision kernel. So they assume, for example, the first assumption is that those particles, they are uniformly distributed, okay? So we assume that each position here is equally probable. So this is an assumption, a strong one, by the way. And the second one, so even if we have a turbulent flow, the assumption is that the collision is driven by the fact that this large droplet, for example, here sediment faster than the small one, okay? And then it will sediment faster and then collect the smaller droplets. So the sedimentation, so the collision is induced by this differential sedimentation in still air. So I mean that there is no flow here, no underlying flow. They are just sedimenting in still air. And okay, so this is the first assumption, but this leads to a paradox. So we can call this what we call a paradox of warm cloud physics. So the paradox is the following. So as you just form the cloud, so we have an early stage cloud droplet. So they have, when you just activate a droplet, so these droplets are very small. So the size is of the order of 10 micrometers. So it's really a tiny object. And to generate a raindrop, so a raindrop, the typical sign of a raindrop, of a drizzle drop, right? So this is around 1 millimeter. So the increase in volume is 10 to the 6th power. So you need a lot of collisions, right, between small droplets to generate such a large raindrop that you feel in your skin, right? And if you use this classical collision kernel, the typical collision rate is 1 collision per hour. Okay, so you have to wait 1 hour for 1 collision. So it's a long time. And how can you explain the onset of rain showers after 20 minutes? So this is a kind of thing that you see during summer, that the cloud is formed, right? And you wait for 20 minutes and then it rains, okay? So there is no way by using such a classical collision kernel to predict such a rain, okay? So then there is that's the paradox. So there are many ways to explain this. One of them, in all of the ways, of course, there is turbulence behind, okay? But one aspect I will explore here is the following, that turbulence induces a clustering of droplets in a cloud, okay? So the assumption of a uniform distribution of droplets is not a good one. So if you have turbulence, the cloud will look more like this than like this, okay? So here, what happens is that we have more droplets together, and we have an enhanced probability of droplet collision. So this kind of distribution would accelerate the rainformation. Okay, and of course that the problem is that look that everything here is happening inside our grid box, and we have no information about this. So we have to do a kind of a probabilistic description of this problem, right? So sorry. And then how can we do that? So this is, imagine that this is a very complicated many body problem, right? So think about statistical mechanics. So we have a many body problem, many particles immersed in a flow, and they interact through a complicated flow. So we can do some statistical considerations, right? And try to reduce this many body problem to a two body problem. So then consider for example, a droplet pair. So we have two droplets here immersed, surrounded by all the droplets, and everything here is immersed in a turbulent flow. Okay, so here the parameters here are the separation between those droplets and the relative velocity between them. Okay, so then a statistical description would be based in terms of a probability density function. Okay, so the probability density function here is P of R, W, and T is something like this is more or less the probability that the distance between these droplets here, they are in this interval, in infinitesimal interval, and that the velocity, relative velocity, is in this interval. Okay, so this is a way to represent this statistically, and of course this is just a characterization. And we need to introduce the dynamics. Okay, we can use another arguments, right? That this evolves according to this or master equation, but this is that is abstract here, but includes all the complex dynamics. Okay, so I'll need another hour here to explain the details about this equation, but it's not the idea here. Okay, so then the idea is how to construct this complex dynamics. Okay, so once we a good construction of this operation L, right, should recover two main mechanisms that we see. Okay, so then what are the main mechanisms that will generate this turbulent clustering? So the first one is sorry, I have some. So the first one is the centrifuge mechanism. So it happens when we have low inertia droplets. So this is a typical case of a cloud. So low inertia, what is the issue? So if the droplets, they have no inertia, and here we have, for example, that the turbulent flow has a vortex, right? So imagine that you have a rotating flow here. So if the droplets had no inertia, they will exactly follow the motion, okay? But since they have a low inertia, so some inertia, so what happens that those particles that will be expelled from the center of these vortices by centrifugal force, okay? So of course you can imagine something that is rotating here, and then it is expelled by centrifugal force. And it can of course meet another particle that comes from, that has been expelled from all the vortex somewhere, okay? So then the mechanism of centrifuge, mechanism of clustering is exactly this, right? So that inertial droplets, they accumulate in regions of low vorticity. So vorticity is associated with the angular velocity in a fluid flow and high strain. So this is, if you look at this, so this void of vortices here are regions where we have high vorticity, right? So high angular velocity of the fluid flow. And here where they accumulate are regions of low angular velocity of the fluid flow. So we have a kind of this clustering, okay? So some authors also has explained this initiation, so this enhancement of droplet probability of collision, right? So they are clustered here in the case of a very high inertia droplet. So I would like just to mention, so what we call this is the caustic activation of rain showers. So this happens when we have high inertia droplets. So look that here we have a distribution of particles of droplets in a turbulent flow, And this here more in red, right, are regions where they are accumulated, right? So we have some singularities. Singularities, I mean that the velocity, if you consider that the field of the particle velocities, they are singular at those red points, because particles from different parts of the flow, they meet at these points here, and they have different velocities, right? As the velocity field associated to the particles here are kind of multi-valued functions, okay? So then we have these very concentrations with this characteristic pattern here. And we call this caustic because it's very similar to the caustics on the bottom of a swimming pool, right? So here we have a focus of lights, right? At the bottom of the swimming pool because of the waves at the surface of the water, right? And then you see these very similar pictures. So this is an interesting subject, right? So, but not exactly, in my opinion, is not the good reason for. It's not very applied to clouds. But the previous one here, yes. Okay, so we have a centrifuge mechanism that really increases the local concentration of droplets, and the probability enhances the probability of collision. Okay, so look, that to solve the paradox, we have to solve this complicated problem. Okay, and then obtain the right probabilities, right, with the enhancement of probabilities. Okay, so okay, so this the second kind of issue, right, that we have here, and the last one. So we have a third aspect, and third kind of a paradox in meteorology is the persistence of mixed phase clouds. So what is a mixed phase cloud in opposition to a warm cloud that we have mentioned, right? So in a mixed phase cloud, we have already ice crystals. Okay, so a mixed phase cloud is, look that we have a cloud here, and that occupies some different layers in the atmosphere. So we have here a layer in the atmosphere where the temperature is between 0 and -40 degrees Celsius. Okay, so in this kind of a situation, this layer, we may have a mixture of supercooled droplets, okay, and ice crystals. So this is a mixed phase cloud. Okay, and what is the issue here? So if we look at a mixture of supercooled droplets and ice crystals, so look at this as a heterogeneous thermodynamic system. Okay, so what happens is that we know from thermodynamics that if we are at the temperature and pressure of the tripole point, so water in form of ice, liquid, and vapor, it can coexist, right? So there is a very coexistence point where they can live together. The problem is that when you go at smaller temperatures, so this is exactly when we have here. So look at the temperatures like this, and this dashed line is a continuation of the liquid line. Okay, so this dashed line is the line of coexistence of vapor and supercooled liquid. And here the solid line is the coexistence between ice and vapor. And you see that for small temperatures, the equilibrium pressure for ice is smaller than the equilibrium pressure for supercooled. So then what happens? That we cannot expect equilibrium here. So this is a thermodynamically unstable. So what happens? It happens that supercooled droplets, they tend to evaporate, and this vapor is taken by the ice crystals. Okay. Then what happens is that ice crystals, they grow at the expense of the surrounding liquid droplets. Okay, so then what happens that eventually this ice crystal grows very fast, and those droplets here, they disappear. Okay, so this is the thermodynamic instability, a conditional condensational thermodynamic instability in such a mixture. Okay, and this is the main mechanism for example, for rain in mixed phase clouds, right? So that these liquid droplets evaporate, then the ice crystal grows very quickly, and then sediments. Okay, and of course it can attain the ground in the form of an ice particle, or it can melt along the way, right? And then you have a liquid rain, right? Not a nice crystal falling. Okay, but the issue is that we have here this thermodynamic instability, and this leads to another paradox. Okay, so which is the following. So a mixed phase cloud persists for many days. So at a time, despite the inherent instability of a liquid mixture. Okay, so there are some mechanisms that counteract more or less this instability. Okay, so this is not like this that the instability appears here and then it immediately glaciates the cloud, and then we have ice only. Okay, so of course this is something that we need to explain. One of the possibilities is the following. So we look at inhomogeneities at small scale. So theories that predict that observe instability, a strong instability, are those theories that inside the grid box of our simulation of a cloud, so they assume that we have a very homogeneous system. Okay, so I assume that the cloud droplets and liquid ice and ice here, they just see the same temperature field, the same vapor field, and everything here interacts very strongly. Okay, so that the ice here grows at the expense of liquid droplets. But in reality, we may have some inhomogeneities, right? That at scales that are not represented in the models. So we may have some kind of clusters of ice, right? And clusters of liquid droplets, and they do not interact so strongly. So I mean that this droplet, this ice here, will not grow at the expense, for example, of a cloud droplet that is far away, something like this. Okay, so then we need somehow to represent the physics here to try to explain this persistence of mixed phase cloud, right? Then what is the idea that is what we are doing at our group? That, for example, so here is more or less the picture. So imagine that we have the temperature distribution here is not a distribution which is very homogeneous, right? So the growth of cloud particles depend on the details of the temperature field. So I mean that that they don't see that the droplets here and ice, they don't see exactly the same temperature field and the same vapor. Okay, so they are inhomogeneities here. And to describe these inhomogeneities here, so of course we are not able to simulate it in detail. So we have to use again stochastic or statistical description. And let's say that we introduce here a probability density distribution for the temperature, right, at a given point. So that this object here gives us the probability that the temperature at this point here is in this infinitesimal interval. Okay. And of course, again, we have to introduce the dynamics. And there is an evolution equation for this probability distribution. Okay. But we again write here in terms of this very abstract form. And I repeat here that I would need another hour to explain how to derive such an equation or how to model this. But this evolution operator here incorporates complex dynamics. Okay, so incorporates turbulence and the interactions between those objects with turbulence. So this is the big challenge, right, of this modeling. Okay. Okay, but why is that important? Okay, so look that if this cloud here glaciates or not. Okay, so if this liquid droplets will disappear and we'll have a huge ice crystal here. So I mean, we glaciate the cloud or the phase partition. So the amount of liquid water that we have compared to the solid water. So it has very large implications in weather forecast, in climate change simulation and predictions. Okay, so why? So look that this is here what we call a stratocumulus cloud. So this is photo of a stratocumulus cloud formed from above. And this is a huge stratocumulus cloud. So it covers a huge area. Okay, and look that the fact that how much ice or how much liquid droplets we had here has a strong influence on how this cloud here will reflect radiation or allow to pass radiation from space. Okay, so I mean that the Earth radiation balance delicately depends on the phase partition in mixed phase cloud. Okay, so if you make some incorrect predictions on the phase partition, if your model creates too much instabilities, right, the thermodynamic instabilities, so we have the wrong result, the wrong radiation balance, and it has a strong influence in climate models. Okay, so this is a very important subject. So then an attempt to simulate this based on this model is the following. Okay, so look at here this cloud. If you see from a side view with something like this, so this is the ground. Okay, so the cloud is kind of a stratocumulus cloud. There's a kind of a layer here, and we are interested in the amount. So this is the plot of the amount of condensed water. So condensed water is the amount of liquid and ice. So this is a typical figure, right? So that it grows linearly and has a maximum value here at the top of the cloud. Okay, but of course this is here we have liquid and ice. So a model that match to observations, right? So here this is the cloud base at 1,000 meters here. So this is the cloud base. It grows linearly, the total one. But look that there is a difference, right? So we have ice, which is the small portion of that. So we have here, this is this ice curve, and here's this is the water, the liquid, right? The liquid part. So then these are something like observations. So we see that the mixed phase cloud here persists, right? So we have really a mixed phase cloud, no glaciation, okay? But when we do a very naive scheme, right? So look that this is, if we use a non-turbulent case, you see that what happens. So above the cloud base, so we see that there is no ice. And when this ice appears, it consumes all the vapor, okay? It takes all the water from the liquid. So the liquid here goes to zero, and here we have only ice. So we have really a glaciated cloud here, okay? If we have in the model no account of turbulence, no account of variability of the temperature field, okay? So this is unstable, and that's it. So the model that we have presented is that the stochastic, right? That I mean the stochastic and probabilistic, and including the effect of turbulence. So here we have a cloud which is really mixed phase, not glaciated. So we have some ice together coexisting with some supercooled droplets, okay? And look that this cloud here will completely radiate different or from this, okay, the balance. And here I repeat again the model, which is matched to observation. So this is a model that has just adjust to get the right answer, okay, but without any understanding. Here, to derive something like this, we had to do some effort to account for the turbulence effects, okay. So then the main message is turbulence is a key mechanism, okay, for maintenance of mixed phase clouds, okay. So this is one approach to the problems. Of course, there are many others. So I think that it's a good time to finish. So I would finish something like this, that I would like, not summarizing the whole talk, but that I would like you to have in mind is that clouds, so why they are complicated. So there is a complex interplay of microphysics and turbulence, okay? So very difficult subject in physics, okay? A second point is that numerical simulations without understanding threaten scientific progress. So I mean that the tendency now in climate models and in weather forecasts is to do simulations using higher and higher resolution. And this is not a good practice, okay? So what, of course, good resolution is something, but we also need to parameterize or to put some information at the scales that we are not able to represent. And there we need to put a lot of physics there. There are a lot of physics and a lot of theoretical effort, okay? So simulations alone and many data and machine learning, something, nothing will be better than a good theory, right? And And related to that also, but I mean that cloud dynamics and weather forecast and something related to this, that's climate change, is a problem in theoretical physics. Okay, so theoreticians had more interested in string theory and quantum gravity and stuff like that, but we have a big problem to be solved in classical physics, right? Which is very challenging. Okay, and that's my message for you today. And thank you very much for your attention.
Thank you very much, Mr. Gustavo, for introducing us to the world of cloud simulations. But I have one question. To be honest, for my field is totally different than the climate simulation. So I didn't even know that this is kind of this even issue in problem in theoretical physics. But coming back to your simulation that you presented to us, could you just say us more how do these simulations agree with real clouds observations? Are there any outsiders or maybe non-standard behaviors that you can't explain? Could you say more about it?
Yes. So this is of course. Look, that this is also a challenge to compare simulation with observations. So you can imagine that observations of cloud properties is really a very difficult task. So we have some standard experiments. And we try to combine, right? So I'll put it in a very general. So the problems that we have normally is that some simulations, they, for example, in field observations, you see rain after some time, and the simulations you cannot produce rain. So you have no rain at all. So this is the main problem that we can that I can mention to you. Okay.
Okay.
And the problem is that how to generate rain. So you're trying to adjust things, right, without understanding the physics. And this is the dangerous situations. We are still trying to close the problem. So this is the problem of generating rain, and is really complicated. Okay, so please believe me that.
I totally believe you. Thank you very much for that answer. And maybe another remark. You said something about improving the climate models via the simulations. And maybe we could say something more about what do you think about the future applications of the simulations that you presented to us. Maybe one day these results are made us to, I don't know, that we'll be able to manipulate weather, or maybe any other science fiction stuff. So, Mr. Gustavo, I see that there's some technical issue. Maybe we'll wait just a second.
You hear me?
Oh yeah, you are back. You are back, I see. Mr. Gustavo, do you hear us?
Now I can hear you. Yes, it was.
Okay, perfect. So there were some just technical issue. Have you heard my question, or should I repeat it?
So I understand that if we will apply some time in a climate model, right? So this kind of simulations.
Yeah. Like, but you said something about the improving the climate models, but I will go farther. Maybe maybe let's go to the kind of science fiction field, that manipulating the weather or something like that. What do you think about it?
Oh yes, that's a good point. So look, that manipulating the weather is something that you probably have heard about cloud seeding, right? You probably have heard about cloud seeding. Is that cloud seeding is the following. So you can take an airplane and spray some particles to induce the rain. Okay, try to produce rain. So, and this is, of course, there's a lot of applications. So everyone tried to do it, right? In some places where we have problems like Israel right, when it's very dry, or something that you want to host the World Cup and you want to avoid rain during the matches, right? So then you try to manipulate weather in this way to produce rain or avoid rain, and then those clouds seem that they don't work very well because this is a very complicated microphysical problem, right? And the interactions with turbulence, as I mentioned. So this is and of course a better understanding of what is happening at small scales will improve this kind of procedures, right? So we can give you a better protocol to generate rain or to induce rain by cloud seeding, by spreading particles in the atmosphere, right? That will nucleate droplets or that will induce rain. Okay, so this is one kind of application that it comes to me now.
Okay. Thank you very much for your answer. Thank you very much for your very interesting lecture. And thank you that you agreed to visit us on ScienCon Online 2022 and talk about and show us more, tell us more about the climate and clouds simulations. For those who are watching us online right now, in 5 minutes we're gonna start, or maybe in 10 minutes, we're gonna start the final presentations of our participants and the final results of the work. So we can stay here, but not exactly in this live transmission. There is another part that you can find on our ScienCon Online YouTube, and just we're gonna start it in 10 minutes. So see you there. And Mr. Gustavo, thank you very much for this presentation.